Dr. Ekta is a research scientist at NVIDIA Research in Silicon Valley, where she focuses her research efforts on designing deep learning algorithms that automatically evaluate the quality and authenticity of visual media. To this end, she also explores topics related to accurate modeling of the different aspects of the human visual system, generative models for images, and deep learning algorithms that learn from noisy or limited data. Dr. Ekta is a recipient of an AI grant, a Google Compute grant, two Outstanding Teaching Assistant Awards at UCSB for her teaching efforts in deep learning, and a dissertation fellowship from UCSB. Her work on automatic image quality assessment has invited a global audience across industry and academia and forms an important baseline in the research community. Also, Dr. Ekta also takes a keen interest in mentoring and teaching students who are interested in AI, and in her free time enjoys running long distances and painting misty forests. Okay, so yeah, over to you, Ekta.
Thanks, Varda. Okay, hi everyone. It is, like I was saying, it's so nice to be here. Today, I'm going to be talking about AI-generated visual content, talking about some algorithmic milestones, and also closing with merits, demerits, safeguard mechanisms against potential threats and things like that. Okay, there you go. So let me minimize the speaker so I can see my screen. Okay, so before I begin, let me establish the context of my talk by defining some of the keywords that are related to the subject matter of my talk. The first term is, I imagine, something that every one of us has heard in some context: artificial intelligence, which is a term that is used to refer to algorithms that try to simulate aspects of human intelligence. And within the broad field of AI, my specific area of study falls under computer vision. This field of study aims to enable computers to understand the world around us through cameras. And cameras is a broad term here. It can refer to not just the visible camera, but like infrared cameras as well, for example. And the last term, which is a main consideration of my research so far, is deep learning, which refers to learning computer algorithms that can hierarchically process data, typically perform like several million computations for each instance. It's a very popular data-driven model design tool. So yeah, that's the context of this talk, just in case we have diverse backgrounds. My plan is to keep it high level, try and make it a bit more accessible across backgrounds, but feel free to ask me clarifying questions. I am not able to see the chat, so just interrupt me if there's any questions at any point. Also, now I'll begin with a recap of my journey so far.
Hello.
Yes.
Am I audible?
Yes, Dave, hi.
Am I audible?
Yes, Dave, I can hear you.
Yeah, thank you for giving the opportunity to us. So, actually, I'm new to this topic. My question is it's a basic question. Is artificial intelligence and deep learning is there a negative side? Like, can they take over humans? Like it maybe sounds some fantasy, but is that really a good thing to empower them? So that is my concern and question.
You'll see as we discuss about what it means to, for example, train a neural network, it's nothing but a combination of multiplications and additions and some non-linear operations. It is a little bit, I would say, science fiction-y to kind of say that, they'll take over the world and it's something to be scared of. AI is its intent, as the way I see it, is to enhance some of the different aspects of our life, which are kind of boring. For example, automating human assistance in the form of like home robotics, assisting, for example, on a conveyor belt like setting where you want to monitor each item. So the tasks which are repetitive and can be kind of exhausting for humans, AIs can do it well. And the reason for that is like they are kind of dumb. They just learn from the data that's been shown to them. So there's not a risk of they'll take over. But there is a risk that is something worth considering with regards to generative deep models. And that is precisely the purpose of my talk today. So let's keep going. You'll see. But the short answer is we shouldn't be afraid of AI, like, in the sense of like it'll take over the world. That's not like, once we understand how it works, it's actually fairly silly or stupid or dumb, because it will continue to learn just from the data that's been taught. Like, so it's not really as powerful as human intelligence. The intent behind most of the AI tends to be to assist humans, not take over. So hope that satisfies, Dev.
Yeah, thanks.
Sure. Okay, so let me begin with a recap of my journey. Aside from just like an introduction, this is more of an there's a more important intent here, that is to provide a bit of a context to my discussion today and introduce some of the keywords. But of course, this is just one of the many steps someone could take towards a career in AI. A large part of my last decade was spent in academia, beginning with pursuits of a bachelor's degree in electrical engineering with a minor in CS, followed by a master's at UCSB and then a PhD. I did manage to maintain a good industrial contact throughout my various years in the last decade, and and this decision kind of has proven to be a very enabling one, and I highly recommend it to someone considering a career in AI, because advancements in AI, my observation has been that they're pushed forward very much by industry as they are by academia. And this seems to be somewhat of a unique thing with computer vision and AI. And I noticed that some of the most impactful research often has collaborations across industry and academia. So, and for me personally, industrial collaboration on projects very much helped me, shape my research identity and allowed me to explore diverse topics, which you'll shortly see. But now looking back, everything's come together quite well after a lot of meandering. And I think that is important for us to understand, what alternatives are there and what's something one truly might like in the field. So what began as a mild interest in signal processing led to an internship exploring how computers can digitize images of text documents. I then moved to exploring different kinds of photography techniques. And this is not capturing pictures with a camera. It's more about exploring algorithmically, how light can be manipulated, for example, to do HDR imaging or capturing different perspectives of light with photography. So light field photography. So it's very much get input data, process it in Python, get some insights, see if you can improve the experience of the whole image viewing as a result. So it falls under the domain of computational photography. And after this, I kind of made a shift. I started to explore how we can, for example, capture motion in videos and transfer it to related images. Let's say I look at a waterfall video and I transfer it to a still image of waterfall to animate that waterfall still image. So like image animation using motion driven by related videos. And after a couple more projects in image processing, I began to realize how difficult it is to design an algorithm that can automatically identify a good quality image. For example, if I show you two versions of an image, you can tell me clearly which is of a higher quality. Designing algorithms that aid computers to do this task automatically can enable massive progress across so many image processing, computer vision, graphics related tasks. However, up until 2018, aside from a few promising smaller scope efforts, a solution to this problem remained quite elusive. And existing algorithms are quite inconsistent, as we can see here. This is just a list of existing work. They're quite inconsistent with human perception of quality. Part of the difficulty lies in the fact that human vision is very complex, and modeling human perception of quality is even more difficult. For example, it's much more tougher to capture training data for this task. It is very difficult to ensure that there isn't some noise in the training data that you capture. So I'll talk about those later, but there's an added level of difficulty because quality perception tends to be subjective. And this is the case even though quality perception is like very intuitive to humans. So this problem of designing perceptually consistent image quality metrics excited me a lot and became one of the focuses of my thesis. It also led me to explore two complementary questions pertaining to quality evaluation. First, how can we make a computer's perception of visual world much more consistent with human perception? And second, under what conditions do we not want computer vision to be consistent with human vision? Of course, like these are like, very difficult and like broad questions. And that's a good part. Like, it means I have enough to think about probably for the rest of my life. But as a part of our discussion tonight, I will be touching upon my insights so far for these two questions. Now, I guess just to wrap it up, along the path of exploring these questions, I pursued three more research topics. First, around designing algorithms that can automatically draw realistic images, or in technical terms, generative models for images. This is a very interesting class of AI algorithms. They learn to understand the visual world in a manner that allows them to draw it and recreate it. And their use is becoming increasingly popular amongst AI artists, like the movie industry, and I'll touch upon that next. And then I also studied how to model human visual attention and algorithms that can detect like, computer generated content, even when that content is like, very high quality and humans can't tell that it's like, artificial content. It looks very realistic. And yeah, so fast forward this year, I'm continuing to pursue this journey. All right, so now we're caught up on what's happened in the last decade almost, but more importantly, we understand some of the very exciting challenges in the field of AI that I'm concerned with. And and now we're also kind of warmed up to the context. We know some keywords and kind of like, some of the challenges around all of these problems. So with that, now my plan for the talk is that like, I'll provide you a broad overview of deep generative models for images. I'm happy to also discuss technical details, probably in offline conversations or in follow-up questions on email. Feel free to like, ask me. But my aim here is to keep this talk quite accessible. So it will be kind of very high level. I will discuss some of the important milestones on that topic. And for example, the rise of perceptually consistent image error metrics to train deep neural networks. And then I will discuss like, what are the advantages and threats posed by, to kind of go back to Dave's question. What are the advantages and threats around some of these deep generative models? And then I will kind of discuss safeguard mechanisms, and which is a very active area of research. So, and also very interesting because it answers the question in under what cases do you not want computer vision to be consistent with human vision? So we'll touch upon that. Okay, so a lot needs to be covered in the next 40 odd minutes. So let's jump right in. Our overall aim is to approximate a function G, which is formulated in terms of parameters theta and some mathematical operations using theta and the input. So given an input X, the predicted output is y hat. And let us say that the expected output, which is what we want the model to predict given input X, is y. Okay, so these are like what we're going to work with. And our aim is to tune the parameters theta such that the error between predicted output of the function, that's y hat, and the expected output is minimized. So like we want to tune theta so that we get y hat to be as close to y as possible under some definition of what's close. So that's the loss function in machine learning jargon, or it's the error function or optimization objective. This formulation of like, it's a very standard formulation for any kind of data-driven model design. For example, let's take an example of like fitting a line to a set of like blue points that are shown here. we could adopt a similar approach, fit this problem of fitting a line to this framework here. And in that case, the formulation for G could be mx plus c, parameters could be m and c. And we might decide that the well-fitting line is the one that minimizes the squared error between y hat and y, and we might optimize the parameters m and c to achieve that objective or error bar or loss function. So overall, this is kind of a general framework for data-driven model design. For now the more interesting question is, when the data is very complex, such as when you have images with several pixels and each pixel has 3 numbers from 0 to 255, those arrays of pixels are organized to help the computer make sense of the world. And we want to train the system or find suitable parameters theta to help them do that. So I guess, yeah, so then for a more complex model for images, let's say if an input is an image and output is a prediction of what object is shown in the image, then the function G would need to be fairly complex. And this is where, like deep neural networks and more advanced like loss formulations can come in. So what is a neural network? Simply put, a neural network is a mathematical construct. It represents a function that's designed to apply a hierarchy of weighted sums and nonlinear operations on the input. For example, in this seemingly complex picture here, each edge represents multiplying the input with a scalar. And the edges converge to a node where they are added up, whatever is the weighted combination that's added up, and then you apply a nonlinear transformation to it and then pass that result of nonlinear transformation on to the next set of nodes. So this is literally like what kind of neural networks tend to do in one of their popular formulations. And then then, for example, the weights would be the parameters, and we want to basically try and optimize the parameters to minimize some formulation of loss, right? So, that's what we term like training a neural network. It's the estimation of the parameters that in the network, which is the weights, and doing so in a manner that minimizes the loss function. And we have a bunch of data points which we are going to kind of use. So take a batch of input, pass it through the network or the function G. I call it network, but it's literally just a function. It's a formulation where you have these hierarchy of operations, and using that function, you pass it through it. That's called the forward pass, and obtain a predicted value. And you're going to basically compute the loss and update the network's parameters to minimize that loss, which is something, one way to kind of do that is through something called gradient descent, where the training signal or the signal that tells how much each parameter needs to change is obtained from gradient of the loss with respect to that parameter. But if it's kind of seeming very it's too complex, all we need to know here is there is a function which is a specifically formulated function in the form of like hierarchy of operations, and we want to have that function behave in a certain manner which is dictated by the input output pairs x and y. Now, the complexity of these models can be quite high, and the amount and it can amount to like several million parameters. I'm just giving you one example here with my cursor. It does seem like this is performing a lot of weighted combinations and non-linear operations. So then we want to estimate all of them, and as a result we want the size of the training data set that we need to reliably estimate these parameters. It can be very high. For example, ImageNet is around 14 million images. It's a data set which contains images and corresponding expected value y, which is the annotation on what object is shown in the image. So a model trained on ImageNet data set would be able to take the input image and predict what is the object that's shown in the image. Typically, when dealing with images, we replace exhaustive weighted combinations with like series of convolution operations, which is nothing but a filtering of the image in multiple stages. And the construction of the filters are something that you want to learn. That's the parameter. And so, like, the exact training mechanism, the loss formulations, all of these are like very critical choices. And a lot of research has gone into designing it well. The availability of large-scale data sets, parallel processing, and advanced algorithm design has made AI kind of where it is right now, where all of us know about it, starting to have some part in our lives in some manner. For example, if you're using a phone, you're probably kind of leveraging some of the AI algorithms in the process. So a combination of these factors around data, model design, and parallel processing, for example, thanks to GPUs, is what's bringing about this revolution. And kind of these are the basic components. So to sum up, learning to accurately predict outputs for inputs such as images, we need a complex function G. We need an effective loss function and an effective training strategy, and a large training data set containing pairs of input and, when possible, to know the expected output. Now, let us say we have these ingredients. What kind of functions can we learn? The answer is, given enough of the three resources that I just said, you could train a deep neural network to perform any task. And they are famously coined as like universal function approximators for that. It is, although still a theoretical possibility, there is a lot of engineering and design that needs to go into getting that to be a reality. Okay, so now, for example, let me give you another example of a task. Let's say, given a noisy image, you can learn to denoise it, meaning that remove the grains that are shown in the image. You would do that by performing series of filtering on the image, and the filters that you want to apply to the image, you would learn through the whole training process that I just described. So in this case, input would be the noisy version. So X would be the noisy images, and Y would be, for example, the pristine images. There are other popular things you can do with an image using deep learning based training. You could, for example, create artistic effects where, for example, an input image is converted to like starry night scene type setting, where the image is still there, but it kind of looks like it's taken the texture and the color tones of starry night painting, or even Monet paintings. So that's kind of called style transfer. It's again something that involves one image as input, another expected image as output. And what you try to do is compute the loss or like an error measure between the two images. And then you use that as a way to derive the training signals or the gradients to train the neural network. So carefully thinking about the error or the loss formulation for image-based tasks is one of the critical choices. Designing error metrics that are consistent with human perception goes a very long way in effectively training some neural networks for some of these tasks. And if time permits, I will talk about one of my previous contributions on the topic of designing perceptual metrics. It was a paper I published in 2018. It talks about one of the first perceptual metrics that was that showed the highest degree of consistency with human vision. But know that this is it's intuitive to us, given two images, you can tell which is kind of visually closer to another, but it's very difficult for computers. Yeah, it's a very active area of research. So, okay, so now what do we know? We know that we can train a neural network. We know the ingredients that go into training it, and some tasks which neural networks can perform effectively. So now let me go a step further and talk about so in terms of designing appropriate loss terms and training process, what can we do? So let me tell you about a very interesting class of deep neural networks, which is called the generative models. They learn to do something that's seemingly impossible. So given an input vector X, which can be a set of numbers, the deep neural network G which we will now call the generator. Looks like Pranjal has some intro. Okay, thanks for muting. So yeah, so as I was saying, given an input vector X, which is a bunch of random numbers, the deep neural network G, which we'll now call the generator network, it can be trained to predict realistic looking images of a specific class, such as face images. So the first time I heard about it, I was like mind blown, like how does this even happen? Effectively what the network is learning to do is it's transforming one random distribution to a distribution of images. Pick a random number from the distribution of input vectors, and you will be mapped to a corresponding input image, which is very realistic. So how does that even happen? To achieve this, the training process brings in another neural network, which is called the discriminator network. So it's the discriminator network. It's not a loss function anymore, where you have some notion of computing error between two. It's a full-blown neural network which is going into the loss formulation itself. And now the job of this network is to classify whether an image is from the real world or is it from the set of images that the generator has created. So this kind of setting is called a generative adversarial network. And these two networks are trained together in an alternating manner. So like one training iteration, the generator will improve itself to generate images. And the next training iteration, the discriminator will try to improve its classification accuracy to tell apart generated images from real images. And the challenge for the generator is to try and fool the discriminator. So generator wants to create an image that can fool the discriminator, and the discriminator wants to keep improving its parameters so that it can always catch the generated image. Think of this as like a game or an adversarial match between like a forgerer and a detective. The forgerer wants to keep improving their skill and create new and new forgeries that can also fool the detector, and the detective wants to see the samples from the forger so that they can kind of keep the knowledge updated on what the forger is doing. By replacing the loss function with this learnable discriminator and training both generator and discriminator alternately, what happens is eventually generator starts to generate samples that are very close to the real world samples. As you can see at the bottom left here, it's an output of a network. It's not a real face that you might attribute to any person in the world. It's an output that's been neural network has learned to create face samples from the distribution of what they think humans would think of as real faces. So very impactful, and all because you have switched out the loss formulation and brought in another network, and both are being trained to kind of beat each other. Ultimately, the generator wins. But if you look at the fine-grained information, like at, for example, very low-level pixel values, which to the visible eye, they're not there, discriminator network is still able to catch the generated content. So okay, so a lot about generative models for images. Now let's see some examples, to appreciate how powerful they can be. Here are some more examples from a GAN model, or a generative adversarial network model, which is dubbed style GAN. None of these faces that you see here, they are real people. These are just like facial renditions dreamed up by the GAN. And we can see they kind of, to a human eye, they look very realistic. What more can we do with GANs? Now I want to kind of draw our attention to an interesting aspect of generative models. Generative models are great. Like, for example, these can be actively used in movie industry, for example, to keep let's say some actor passes on at some point in future, but if their facial model is kind of maintained, you can kind of keep generating models of it in future. So like you can create timeless actors. You can help touch up artificially the faces of the actors to make them look a little bit more cartoony. You can dream up new actors. Some of these people could be like some of these artificial faces could kind of be in a synthetic movie. You can, I'll talk about it in a minute, but you can enhance video conferencing experience a lot through generative models. So there's a lot of good here. And it's a very interesting scientific problem as well. There is a flip side to it as well. So let's start to go towards understanding what that is and what are the safeguard mechanisms. So on that note, another popular application of GANs is expression manipulation. So given a person's face, in this case Obama, you could extract expressions from one video and transfer it to another video. For example, if Obama is like sitting in his living room and trying to kind of give a speech, but he wants the public to see a speech where he's kind of in a jacket, then that's something you can achieve very easily. Here is, oops, I wish that video would play. Here. It's not synced right now. Like, it seems like both left and right video are speaking the different things, but actually the expressions from the left video were used to animate the right, the still image, and then that resulted in the final video that you see those. So if you compare frame to frame, the expressions on the left most video and the right generated video, which is kind of shown on the right, it's kind of exactly the same. I wish I had thought of syncing it. It's quite remarkable if you see it kind of together, but they are speaking the same thing. Only thing is that this is not a video that's short. It's something that's been generated by a generative model. So I think a lot of us could probably think of misuses of this kind of model. One classic one is generating deepfakes using generative models. So in this case, Angelina Jolie is providing the expressions and she is animating the Gal Gadot's face using those expressions to create this face swap deepfake, meaning that the face of Gal Gadot has been, using deep generative models, it has been transferred onto Angelina Jolie, and it's pretty uncanny. Like, you can kind of see no like artifacts by just evaluating them. It looks very realistic. So like, one nice thing could be like the body doubles of actors and actresses could help kind of, shoot the movie, create the experience. But on the flip side, imagine this falls in the wrong hands, like important political communications, which might be happening over video conferencing. That's a very vulnerable channel, and it can be prone to deepfake attacks. So it is kind of a major concern. Just so I make sure I have established the terminology well, a deepfake is nothing but a video of a person's face generated using deep learning algorithms, deep generative models that we talked about, like, for example, a generative adversarial network. So it's a fake which has been generated using deep neural networks, so it's called a deep fake. And it's typically designed with a malicious intent. Like by that definition, even the example here is a deep fake, but it's kind of like an authorized use case. But this case here is kind of unauthorized. Like Gal Gadot didn't ask to have her face, have her face be transferred onto Angelina Jolie. So it looks like she's saying something, but in reality, Angelina Jolie is saying that thing. So it's a malicious use case. There was a very interesting study that happened amongst some of our colleagues at like UC Berkeley, where they studied how AI synthesized faces are perceived by humans, and how much is the trust attributed to those. So for example, if an AI generated face tells you something, and if an actual person tells you the same thing, who are you more likely to believe? That it turned out that just for for whatever reason, the AI generated face was something that people trusted more. And the humans could not tell apart whether that face was actually generated or was it a real face. So that's where we kind of are. We do have a lot of good use cases for generative models, but we do have this threat around propagating misinformation that can easily happen through such technologies if they fall in the wrong hands. So that's kind of our consideration. Like I said, there are some merits, like, low bandwidth communication, like you could transfer just one picture of yourself and like use the expressions to kind of manipulate the picture at the recipient's end. Very low bandwidth communication, like, it can work even on like extremely low bandwidth. You could have, there are several movie industry use cases. It can enhance like a lot of video conferencing experiences, but there are risks around unauthorized impersonations, spread of misinformation, and it does not require as much effort from the attacker, because these models have become so accessible, and they're like it's a common saying I hear amongst like undergrad students from back in UCSB, like, all like when they say like, they're kind of skilled in AI, they say, yeah, I got a network and threw data at it and it worked. No need to know what's happening under the hood to get that to going. That's not the way to go about training a model or even designing like a whole system, but that seems to be a good shortcut, which is something that can fall prey to an attacker who intends to use deepfakes maliciously. So we have to kind of balance our efforts around designing generative models with our efforts around designing safeguard mechanisms with it. And on that note, there's a very promising research direction, which is called deepfake detection. If you remember, in a generative model, when training a GAN, we had generator and discriminator. This area of research is kind of like improving or amping up the ability of the discriminator to discriminate between generated content and real content. So you have seen some flavor of this just in a few minutes ago, a few slides ago, but now let's dive deeper. Is there a question? I see a chat notification. Oh, hold on. Sorry.
I have a question, if you're open to it.
Yes, Chandra.
So one thing that I do not understand in GANs is that you mentioned that it takes input from a continuous feature space, right? And it essentially maps into a continuous manifold after all those weights multiplication, matrix multiplication. How is it that that continuous manifold, all the pixels of those continuous manifold is a real image? Or are they not a real images for all the inputs?
That's a good question. And you're pointing to one of the critical difficulties with training GANs. That is, like, it's such a huge space, right? It's a space with virtually infinite numbers. How is it that you still generate real images? The trick is in constraining the feature space that the network has access to, meaning that you can put like L1 constraints on the weights, or things like ensuring that all the random vectors are having like a unit norm, so they're on like a norm ball. And that way, what you're trying to do is making sure that you don't fall, for example, into one of these like valleys where there is no sense of how to generate real images. So short answer to your question is, it's true that not all numbers, all random numbers will lead to real images, but the way to go about it is to, like, increase the space of random numbers that you feed to the network very gradually. Another way to go about it is to first generate a super small image, let's say 2 by 2 pixel image, which is fairly tractable. Once you have that part done, then you build upon that generative model and add resolution to it. And that's a very popular approach. So, and that's precisely to ensure that it's tractable, the manifold does not blow up suddenly. And as a result, you don't know the behavior of the network in some parts of the manifold. So I do recommend that you read StyleGAN. This does answer that question a lot. And there's another class of generative models called diffusion models. They adopt this strategy of like progressively improving upon the generative process to ensure that the manifold remains controlled in a very effective manner by gradually expecting the quality of the result to improve. And by gradually, I mean like with multiple iterations. So you do forward pass few times, and after that, you kind of gradually add the information to make the image look realistic. So at any point, or any step of that, gradual addition, the network has to do not as difficult tasks like, pull a rabbit out of a hat. Like, it doesn't have to generate, fully good looking images from purely random numbers, but it starts to kind of do it in a step manner. So the task is kind of much more broken down and well stabilized for the neural network to learn properly. Does that answer your question?
Definitely. Thank you.
Okay. But yeah, feel free to, and this is like an open invitation to everyone. Please feel free to kind of, start conversations via email if there is more interest. Like Vardha was mentioning, I do enjoy passionate students who want to kind of keep pursuing this field. There's always a very a dearth of great researchers, and it's always good to have the opportunity to have these conversations with people. Anyway, moving on. Okay, so now we want to detect deepfakes. And this goes to, remember I was talking about, there were two research questions we wanted to consider in this talk. First one is around how do you effectively bridge the gap between human and computer vision? Second is, when there are these gaps, how can you leverage it effectively? Perceptual losses and deepfake detection are kind of like complementary goals, but the aim of deepfake detection is to leverage precisely the inconsistency between human vision, meaning that, let me go back a moment, meaning that these pictures that you see, humans cannot tell that they're real or fake, but there are micro inconsistencies in these pictures which are not visible to human eye. Computers can very easily catch that, and we want computers to be able to catch that, and they are very, very good at it as well. So that's a good news. Or rather, the race against designing deepfake detectors and deep generative models kind of goes hand in hand, and it seems like no one party is like winning the battle. If deepfake detectors are like super good, that's very nice, but like generative models start to become even better, but then deepfake detectors kind of come right on and improve their performance using more advanced techniques in optimization, loss design, and things like that. So yeah, it's a very hand-in-hand research in the research community. And without further ado, let me talk about one of my works. I will probably just talk through two slides. I do have a hard stop in 10 minutes, so I have to kind of give time for question and answers. But yeah, what is a typical deepfake detection pipeline? There are two ways to do it. One is you take, remember the deepfake, we're talking about video deepfakes, really just like the videos that you saw of Obama being reanimated, Gal Gadot being reanimated through her facial appearance and expressions from Angelina Jolie. We're talking about the video because that's like a real threat. So you could go frame by frame, take each frame of the deepfake video and a real video, perform some pre-processing on it, which is typical of a neural network pipeline. And you can do a typical classifier pipeline where you perform feature extraction, and then you have a classifier function that classifies whether the function, like whether the input image frame here is a real or not. And then you can have a time varying prediction of real versus fake, and you can aggregate that to get a decision for the whole network. These kinds of deepfake detectors are actually not, well, let me put it this way. Per frame, high quality generation of images using GANs or any other generative model is actually becoming really good. Like, these kind of approaches might fall prey to the fact that per frame generative models are excellent, and they can probably beat these deepfake detectors. They can fool these detectors, which is bad news for ensuring safe use of such technology. The alternative is to go frame wise. So take all the frames of the video, deepfake or real, perform some pre-processing per usual, then extract the features and do temporal sequence modeling, meaning that look at temporal inconsistencies in facial behavior. These can be micro inconsistencies, again, invisible to human eye, but very visible to the computers. And then use the output of modeling that sequence to train a classifier, and then obtain the real versus fake prediction. Here, there is an important advantage that comes from sequence modeling, and that is, although generative models are really good at generating per frame good-looking results, generating them in a manner that's consistent with human facial dynamics is actually still very difficult. So you leverage the property that there are temporal inconsistencies, probably micro inconsistencies invisible to human eyes, but inconsistencies nonetheless in the generative models output, and you can use those inconsistencies to your advantage. That's great because now you can generate realistic looking deepfake video portraits and things like that, but then you know that you can still catch it if you wanted to through computers, through training like a deepfake detector. So my own work, which was like the last project during my PhD, if you remember from the timeline, that focused on deepfake detection. And what we proposed was, just very briefly, of course, take the video. It's a sequence-based approach, and specifically we focused on like, regions of the face, like, lip motions. Are there micro inconsistencies in that? Eye motion, face motion, things like that. So I'm just showing lips here. And the approach is called phase forensics. In that, what we do is we try to leverage inconsistencies in motion specific aspects of the face, meaning that we don't look at how color changes, how texture might be changing on the face, micro texture, but rather we look at how the dynamics of lip motion in this case are varying across time. Is this consistent between real, and is it what are the differences between real and fake motion? So let me quickly go through it. So yeah, we do isolate motion using specific phase variations. If you remember back from like signal processing classes, Fourier's shift theorem, which says that phase variations correspond to global motion of a signal. That precise insight is used here by capturing phase variations locally in the face and then performing that typical traditional deepfake detection pipeline. So it's kind of a standard one, but the key novelty comes from the fact that we're extracting motion specific features, which enables us to kind of improve the robustness of the deepfake detector, helps achieve like invariance to like appearance changes and things like that. And yeah, so that is just a brief overview of what features we use and how we do the whole pipeline. It is 8:24, so it's like probably closer to 9 in India. So what I'll do is I will skip on the perceptual metric design. It's a lot, as you can see, but let me maybe just quickly just give some concluding remarks. I did have like a lot of slides in just in case we have time, but what have we understood through this like talk or masterclass? We understand components of a deep neural network. How is it trained? We understand some of the very interesting classes of deep neural network based designs, which are around generative models for images. They can result in very uncanny, very realistic looking artificial faces, which is very useful. But then there's also a consideration around misuse, which we want to take into account. For that, we've learned about this field called deepfake detection. Typically, the more popular approaches in the past used per frame approach, but now there's a transition towards modeling just the temporal inconsistencies, because per frame generative models are becoming really great and temporal inconsistencies are very hard to overcome. So deepfake detection using temporal inconsistencies is the next promising direction. And to those who are interested, I would invite you to kind of read more papers on it, reach out if you need some references. And yeah, I would love to stay in touch, obviously, help anyone who wants to pursue this field. Generative models or deepfake detection, both are great. Yeah, and with that, let me stop. We have 4 or 5 more minutes before I have to get going for the day. Yeah, thank you. And if there are any questions, I'll be happy to take them.